This is doing every challenge question part 24. It's chapter 6, which is the second of the three trig chapters in the book 2, year 13 book. Anyway, here we're asked to show that some lengths refer to sec, cosec, and cot, which is nice because I made a super old video on this ages ago, so I could just copy out the slides and do it again. So here's a circle, radius 1 with the tangent here. This angle we can call theta, and then by definition, this length is sine theta and this length is cos theta. That's called the unit triangle when you have hypotenuse 1. Right angle, this length is sine theta, this length is cos theta. Cool. But now we can do a bunch of maths here, because if you take that unit triangle and just rotate it maybe, or maybe I don't even need to do that, maybe I'll just leave it where it is. And now look at this triangle here. Now this triangle here is right angled because tangents meet radiuses at 90. This length is 1. And this angle is theta. Like I said, that's a right angle, which means you have a corresponding side here from cos to 1. So the scale factor from here to here is times by 1 over cos, which of course means to find maybe the hypotenuse, I can do 1 times 1 over cos, which is sec. And to find this length, I can do sine times 1 over cos, which is tan. So therefore, I find a couple of lengths on this triangle, and I can fit them into my picture. This length here was this here, so that length here is tan. And this length here was sec, so this length here is sec. Cool, so that's one of the things I've been asked to do. Just notice how this being tan is kind of interesting if you've never seen this before, because it implies that if tan is the length of the tangent to the point where it hits the x-axis from here, when you raise this angle up to 90, if you slowly increase this angle to 90, so that this point moves around here like this, tan of 90 is of course going to be undefined, because this tangent here is just going to go straight horizontally across, and it will never intersect the x-axis. So that's kind of a good justification why tan of 90 is undefined. And of course, the other thing we can see from this picture is by Pythagoras. Look at this triangle here. 1 squared plus tan squared is sec squared, and you may have seen that identity before because it is in this chapter as well. Cool. Let's do another one then. So if we again look at the unit triangle in the center here, and now focus our attention on this triangle up here. This angle is 90 down there. And now this angle up here is theta, I'm claiming. And I can say that because if that's theta, this is 90 minus theta. This is 90, and so this is 180 minus 90 minus theta minus 90, which I believe is just theta. So this angle up here is theta. And like I've said here, and then of course we've got a scale factor, I think. So, you know, to the side opposite theta, we need to go from sine theta to 1. So that's times it by 1 over sine theta, or of course cosec theta, you could just call that. Which of course means that this length here between theta and the right angle is cos times 1 over sine, which is going to be cos over sine, which is cot. And this length here is going to be 1 times 1 over sine, which as I've said is just cosec. So therefore, this length here is cot from here, and this length here is cosec. And so now we've done all the entire question here. So OC was sec, OB was, or OD was cosec, and this was up here cot. One last thing, of course, is looking at this triangle. You have 1 squared plus cot squared equals cosec squared, which is again something else you'll have seen. That should say a 1 squared. Apologies, I don't know what's happened to that, but that should be a 1 squared, not 12. Next one is sketch the graph of sec. So this is in the book. Cos, of course, just kind of does this. So sec is 1 over that. So 1 over 1 is where it starts. 1 over 1 is just 1. Cos then decreases, which means you're dividing by a smaller number, which means you start increasing. So sec just immediately starts increasing like this, and then it does the same thing down here. So cos would come down here. Cos is 0 here, and then so you're trying to do 1 over 0, which you can't do, so there's an asymptote here. And then when you have cos of pi, that's minus 1. So 1 over minus 1 is just minus 1, and then you make the same arc here. This is quite awkward to draw in PowerPoint, so apologies for that. I could have just maybe copied a picture that was in the book, but whatever. It looks roughly like this. Now it wants me to draw arc sec. And by the way, I was supposed to draw that between 0 and pi, so you can ignore this bit here, and you can ignore this bit here. Again, it was just quite awkward to draw in PowerPoint, and we don't really need them anyway. Now, arc sec is the inverse function of sec. So inverse functions and their function counterparts are reflective in the line y equals x. So I think my only job really here is to just reflect this curve in the line y equals x, and I should be pretty much done. I should also probably state the range of arc sec. The range of arc sec is the same as the domain of its non-inverse. So the domain of sec is just 0 to pi, not including pi over 2. So the range of arc sec is therefore going to be 0 to pi, not including pi over 2. So that's basically that already talked about. So okay, how do we do this then? Well, this point, as I said, is the point 1, 0 up here. No, it's not. It's 0, 1, obviously, you muppet. 0, 1, which means when it's reflected in the line y equals x, you're going to swap the x and y coordinate over. and it will become 1, 0, which is like here somewhere, I guess, because that's pi over 2, which is a bit bigger than 1. So this is 1, 0 maybe. So our new graph, arcsec, is going to start here. Notice how this is also horizontal at this point coming out here. So if we're going to reflect that in this line, it's going to become a vertical. So I think the graph starts here, because again, this part of the graph doesn't really exist. I just drew it because I wasn't concentrating. It's going to immediately head this way, and so our inverse graph immediately heads upwards from here. And likewise this is the point pi minus 1. And so that's going to reflect to be minus 1 pi. Minus 1 pi is up here somewhere. In fact, it's way up here somewhere, right? Because pi is like 3 point something. And that's going straight across horizontally. So again, I think this needs to go straight down vertically. We already argued that the range is between 0 and pi. So, okay, we're starting at 0, that's good, and we're going to pi and immediately heading downwards, that's also good. Now, what else happens? Well, this asymptote, and this is the key thing maybe when you're reflecting graphs in a line, it's not just the curve that you're thinking about that's going to be reflected, everything is reflected. So this asymptote is also reflected. And instead of being the line x equals pi over 2, it's going to become the line y equals pi over 2. So this is going to be our new asymptote going along. And now, so when we're looking about this, does it go, essentially it can't get to this asymptote because just like the original graph never gets to its own asymptote, this arcsec can't get to this one. So is this going to go down and head like this, or is it going to go down and head like that? And now we can argue that it can't go down and head like this, because if it did, it would hit y equals x at some point, and it can't do that because any point which it would hit y equals x, when you do the inverse function, it would also be on y of x, because if it's reflected in this red line, any point that's on the line is going to stay where it is. And of course, we don't have a point in sec that's on the line y equals x, and so therefore this isn't either, and so it has to head over this way. And exactly the same argument is made here. It can't start going this way as well, because then it would hit y equals x, which is not allowed to do. So it has to head this way. And our graph will do this, and that's pretty much the picture. Good, thank you for watching.